Vapor power cycles will be the subject matter of this lecture. In the previous lecture, we had looked at power cycles wherein the working fluid was a gas. There was no phase change along the power cycle. We had looked at three different power cycles in some detail: the Otto cycle, diesel cycle, and the Brayton cycle. And we had just introduced the Stirling engine, Stirling cycle. If you want to analyze any of these cycles, you adopt a same procedure which we demonstrated in three instances. The procedure is as follows. First, plot the changes in the TS diagram and the PV diagram. When you plot the state changes in such diagrams, it gives you the heat interaction and the work interaction. And then you apply first law balances, which we have seen in many cases. So these two diagrams are for Otto cycle. And then you apply the first law balance in general for any of these cycles. It's the same procedure which we demonstrate. And then you get an idea of what is the heat input, heat output. Once you know both these things, you can define the efficiency. In this case, again, the efficiency of Otto cycle is being written out. And then you utilize isotropic gas results to simplify this expression, and then write out the efficiency in terms of certain crucial factors. For example, in this case, efficiency depends upon the compression ratio, which is related to top dead center and bottom dead center. Okay, so and then it is also dependent on K, which is Cp by Cp. Right, so that is the outcome. So how did we arrive at this outcome? Even though there was an open system in reality, that is, there is fuel and air, there is input to the system, and from the outlet, the combusted products are exhausted. You do not really consider such a system. You consider a closed system under the air standard approximation so as to facilitate a simple analysis which gives you efficiency in terms of some crucial feature of the cycle. So that's the approach you take. Then you can plot the efficiency as, in this case, the function of compression ratio for an Otto cycle. However, you see that while you want to increase the efficiency by increasing the compression ratio, there are other associated problems like engine knocking. There can be auto ignition, that is, ignition without the spark plug can also happen. It's called auto ignition. To overcome that, you introduce the diesel engine, which doesn't have a spark plug, and only the compressed gas is just the air, and fuel is injected. Fuel injection occurs. Okay, so but the diesel engines are of lesser efficiency, and for the analysis of diesel engine, we follow the same procedure. You have two plots, TS plot and the PV plot, apply first law balances, apply isotropic gas result, and obtain a expression for efficiency. Finally, we saw a steady flow system. This is the Brayton cycle. So in a real turbine, you have combusted products and then combustion occurring in a chamber. Combusted products are sent to the turbine where they generate work and exhausted and so on. Instead of that, you consider an alternate cycle, which is the Brayton cycle. So here, let's say heat is input into the heat exchanger. The working fluid gets heated up and then goes to a turbine, does work, and then goes to a heat exchanger where it rejects heat to the ambient, let's say, and then there's the compression of the fluid back to the heat exchanger. Okay, so the analysis of the Brayton cycle is along the same approach. PV diagram, TS diagram, PV diagram, first law, balances, and so on. Okay, so this is the essence of gas power cycles. In this lecture, we move on to vapor power cycles, where the working fluid can have phase changes. So this is also inspired by the Carnot Vapor Power Cycle, where there is a phase change, right? So in the Carnot cycle, if you plot in the TS diagram, you have in the process 1, 2, an isothermal heat addition, right, at a higher temperature. And then there is an isentropic expansion in a turbine. And then from 3 to 4, there's a heat rejection in the condenser. And 4 to 1, there is isentropic compression in a compressor, right? So this has certain issues. What are the main issues? This is not so difficult actually to have an isothermal heat addition in a boiler. It is not a challenge. Same thing, this is not also a challenge. 3 to 4 is not a challenge. However, when you come to 2 to 3, isentropic expansion in a turbine, you end up with a two-phase mixture. So sometimes the quality of the steam, that is, there are lots of moisture that is present in this two-phase mixture that affects the turbine. There is corrosion of the turbine and so on. You don't want a lot of moisture there. And then from 4 to 1 also, compression of a two-phase mixture is difficult. So you don't want a vapor cycle operating in this manner. These are the main limitations of a Carnot vapor cycle. Although we started off saying that the Carnot cycle is the most efficient way to obtain work, right? So these are some of the limitations, practical limitations. So you can also operate the Carnot cycle in a slightly different manner, okay, in this manner. However, in this case also, there are certain issues. The pressures involved in this operation, 4 to 1, are rather high. And then if you want to have an isothermal heat addition in the boiler, in this case, 1 to 2, you have to operate at varying pressures. Okay, so that's the only way you can do it isothermally. So these are not operationally convenient. So you want cycles that can overcome such limitation. And the Rankine cycle is a cycle that overcomes all these limitations of the Carnot vapor cycle. So how does a Rankine cycle work? You have an isentropic compression in a pump from 1 to 2. So that is the process shown here. There's a work input via the pump. And then there is, from 2 to 3, there is a constant pressure heat addition in a boiler. Okay. So how do you do that? So you add the heat and you get it to a superheated steam state. Okay. So that is what you do. Okay. So there's a constant pressure heat addition till you reach the superheated state. What is the advantage of doing it this way? So once you are at this point, when you do an isentropic expansion in a turbine, you still are close to high quality steam, right? So you are not somewhere here, right? So you are very close to this point. So you don't have a real two-phase mixture here. And then there's a heat rejection in a condenser. Okay, so this is the Rankine cycle, which overcomes the limitations which we discussed in the previous slide. How do you analyze a Rankine cycle? So if you look at the Rankine cycle, it's a steady flow system, right? We have already analyzed a steady flow system in the past. So we apply the first law of balances. This is the general expression for the first law of balance. And what you need to notice is the Rankine cycle, there are two segments where there's heat input but no work input, and there are two segments where there is work interaction. Sorry, just to clarify, there are two segments here which have heat interactions. There are two segments which have work interactions, right? So this general expression can be simplified in different manner, right? So if you look at process 1, in a pump, there is no heat interaction, there is only work interaction. So the work input into the pump, because it's a steady flow system, the work input is equal to enthalpy difference between this point and this point. And that can be expressed in a better manner, in a more quantitative manner, using the specific volume, and you approximate the specific volume to be at this point. Okay, so that's an approximation. Times the pressure changes. And then you have the other segments. Let's say the boiler. Boiler, there's no work interaction. So the work heat input can be balanced to be equal to the enthalpy difference between H2 and H3 and H2. And the turbine, there is no heat interaction, but there's only work interaction. Work output is equal to H, if you incorporate the sign convention, that is H3 minus H4. And then in a condenser, there is no work interaction, but only heat interaction. The heat output is equal to H4 minus H1, right? So this is just a simple application of the first law. So putting all these things together, work output minus work input is the net work which you get from the system, that is equal to the net heat interaction of the system. From this, we can write the efficiency of the Rankine cycle in the following manner, right? This is the expression. So this kind of analysis we have done in many instances. So all we are doing in these few lectures is applying the first and second law to power cycles. Okay, so different forms of power cycles. So by now you should be familiar on how to utilize the first and second law to do this kind of analysis. So in this case, we will just use the first law. Right. So we have the real cycle, real Rankine cycle, which doesn't operate like that of an ideal Rankine cycle. Let's see why so. So in the segment 1, 2, you want to have an isoentropic compression in a pump, right? So that is never the case. It is a reasonable approximation, but there are fluid friction, internal reversibilities, and so on. There is always a certain increase in entropy. So this dashed line is the real cycle. And then in 2, 3, you won't have a constant pressure heat addition in a boiler. Usually, when you have such change, there is always some heat losses that occurs. You can never so because you're operating at a reasonably high temperature, there are some additional heat losses and so on. Again, you want to operate ideally in 3, 4 as an isentropic process, but again, there is never so. There are certain irreversibilities in the turbine because of which the entropy increases. And when you have a condenser, you just want heat rejection, but there is also associated pressure drop in the condenser, right? So in the process 4.1. All right, so these are the non-idealities that are present in a real system, actual working Rankine cycle. So you can also define the efficiencies based on these non-idealities. Here we are defining the efficiency of the pump and the efficiency of the turbine using the isoentropic efficiencies. So this is the actual work input for the pump, right? So in this stage 1, 2, you can define the isoentropic efficiencies. You assume the same state point at the beginning, but the real state point is H2S, or the ideal state point is the H2S, but the actual enthalpy is actually H2A. Okay, so this is this point, right? So you're not here, but you are at this point. Okay, so rather this picture, you're not here, but here. Right, using that, you can define the isentropic efficiency of a pump. Likewise, you don't have an isentropic operation. Okay, so that's not that's what you want ideally, but that's never the case. There are, because of internal reversibilities, there's an increase in entropy. You can define the isentropic efficiency of a turbine in the following manner. So you start with the same state point enthalpy, H3, but in the real case, you are at H4A, okay, in the actual case, but in the ideal case, you are at a enthalpy H4S. Okay, so based on this, you can define the isoentropic efficiency of a turbine. Again, in a way, when we did exergy analysis, we have done similar kind of analysis. So we are consolidating all this analysis into the Rankine cycle for the analysis of the Rankine cycle. Because Rankine cycle is such a common approach to generating power, lots of work has been done to increase the efficiency of the Rankine cycle. All approaches have a similar philosophy. Again, you can understand the basis from the analysis of the Carnot power cycle itself. So if you want to increase the efficiency of the Carnot cycle, we said that the heat addition should be at higher TH, and the heat rejection should be at a lower temperature. Okay, so this approach also gives you the basis for improving the efficiency of the Rankine cycle. For example, you can have heat addition at or heat rejection at a lower, heat addition at a higher temperature or heat rejection at a lower temperature. Here we are showing heat rejection at a lower temperature. Instead of rejecting heat at this temperature, you are rejecting heat at this temperature. So because of this, there is you end up at this state point. There is a small increase in the heat requirement for you to reach H3, okay? But that is rather a small increase. So that's not a big disadvantage with this approach. However, there are other disadvantages. One is that when you lower the temperature at which you are rejecting heat, you are also decreasing the pressure, right? But supposing this heat rejection is to a cooling medium, which is at some particular temperature, which is less than the temperature of, which is less than this temperature. So you should always be operating at a pressure which is greater than the saturation pressure of the cooling medium, right? Uh, that is important, right? So else you cannot really reject heat. Okay, so that is one of the disadvantage of this approach. That is, instead of operating at a higher pressure, you are operating at a lower pressure so as to have a corresponding decrease in temperature. However, this pressure should still be higher than the saturation pressure of the cooling medium. Else the cooling medium will tend to evaporate, right? So that is the, yeah, so that is the disadvantage here, right? So, I mean, yeah, right. I mean, for the cooling medium comes with the corresponding saturation pressure. All right. So, uh, so you cannot have keep decreasing the pressure to decrease the temperature forever. Right. So there are these constraints that you have to be aware of. And then when you go from this point to this point, the quality of steam decreases, the amount of moisture increases. Correspondingly, there are material corrosion and few other issues uh, in the turbine, right? So this is in the turbine. So whenever you are looking at these changes, you have to keep the four processes that we are discussing. Okay, so if this point 4 is in a turbine, so if you have lots of moisture in the turbine, it corrodes the turbine blades and so on, right? So those are the disadvantage of trying to decrease the temperature uh, at which heat is being rejected. Then there is this other approach of increasing the temperature, right? So you are heating it to even a higher temperature. It has certain advantages. So instead of being at this point, okay, so if you have heated at this point, you do an isentropic process and reach this point. Compared to this point, if you do an isentropic process from a higher temperature, you end up at this point. The moisture content at state point 4 prime is less than the moisture content here. Therefore, the turbines will corrode less. However, when you increase it to higher temperature, there is material degradation in process equipment involving this stream. Okay, so that is the disadvantage. However, the reason why we do all these things is to increase the net work output. So the net work output is this much in this case, and this shaded area in this case. Okay, so both these approaches, lowering the temperature of heat rejection and increasing the temperature of at which heat is being added. Okay, so both have advantages and give you more network. Then there is this another approach is that of increasing the boiler pressure. If you increase the boiler pressure, you are not operating in this line. You are operating in a different line. So you can be at a higher temperature. That is true. And the increase in network that you obtain is this shaded area, and the decrease in network is you're losing this shaded area. Okay, so it's a balance between these two, but it has certain disadvantages too, right? So when you are at state point 3 prime and you have an isentropic process and you end up at 4 prime, the quality of steam is poorer compared to state point 4, right? So there is a greater moisture here, which corrodes the turbine to a greater extent. Okay, so that is the disadvantage. To overcome this disadvantage, so what you can try to do is there are approaches where you operate at a higher boiler pressure and then you can reheat the steam. Okay, so there are other approaches which combines higher boiler pressure with reheating, but we don't look at such processes within this scope of this class. But if you take an advanced class, or there's also some more topics that are elaborated in your textbook, which you can look into for increasing efficiency by reheating. All right. So in general, operating at a higher pressure is useful. So there are also boilers that operate above the critical point. Okay. So you're not you don't go through a two-phase dome and you operate at higher pressure even above the critical point. So these operate in supercritical condition, but they have associated higher pressures have other issues related to the process equipment and so on. Okay, so those say there are safety issues that you have to deal with. So you should be aware of some of these approaches involving the design of the Rankine cycle, because it is very widely used and lot of emphasis is given to improving the efficiency of the Rankine cycle. So in the next lecture, we would switch gears and go from power cycles to looking at refrigeration cycles. With that, I will end this lecture. Thank you.